In this series of videos, I'm going to be covering free body diagrams, which is one of the most important aspects of working with forces. I've switched to a new microphone, so I apologize if the sound level is very off on this video. Hopefully that has fixed some of the issues with the background noise. So in these videos, we're going to be looking at free body diagrams, which I always abbreviate FBD. So FBDs are just free body diagrams. We're going to define what properties they have. What should you always do if you're drawing a free body diagram? And then we're going to look at creating some free body diagrams and interpreting some free body diagrams. So I'm trying to give you some examples here. So one of the biggest learning outcomes with this is representing, that free body diagrams should be drawn any time that you are working with forces. So this is going to be a big representation issue. Now with this comes communication, that there are certain ways to draw them, certain ways to do the notation that actually communicates what you mean. So this isn't a place where you can have a lot of creativity and do it your way. There's one specific way to do it that really communicates certain information about the forces and about the net force. So that's going to be really important. Free body diagrams are going to return in Chapter 6 when we're actually going to start doing some math with forces. Right now we're just trying to create the free body diagram. This is really important since free body diagrams are going to be our jump-off point for everything else we do with forces. So, the importance. I've already highlighted this a little bit, but just really want to stress this. This is your visual representation for force problems. You might also do a sketch. You might also do a motion diagram. You might also do an interaction diagram later when we get to Chapter 7. However, you should always be doing one or more free body diagrams. If you are dealing with forces and you don't draw a free body diagram, you have done something wrong. Now, the reason for this is that this is actually where the physics happens. And part of what I'll try to do in the later examples is to show you that understanding the problem happens when you draw the free body diagram. One of the things that you have to think about is, what are the forces? What forces are present? What directions do the forces point in? And this is important. You don't do this when you start your calculation. You do this when you draw your free body diagram. Lastly, and this connects a little bit with equilibrium that we've talked about in the previous section, is you must figure out, is there a net force? If there is a net force, you should be able to determine which way it points. And this is, again, part of your free body diagram. So maybe you'll have a question where you're trying to determine whether or not there's a net force, but usually that's not the case. Normally you have enough information to know something about the motion to then determine that there is or is not a net force. And again, you should be labeling that on your free body diagram. So the reason all of this matters is that once you've drawn your free body diagram, you can set up your calculations. So you don't want to set up your calculations and then do the free body diagram. It's free body diagram, then calculations. If you've done a good job on your free body diagram, your calculations will really just be one setup step and then math. So obviously the point of this class is not to do the algebra that will actually come up in the calculations. And setting up the calculation should be as simple as reading off what's going on in your free body diagram. So the majority of the physics, the majority of the work that I think is most important is in the free body diagrams, which is why I'm going to take so much time on this video. Okay, tactics box. What do we actually do when we're drawing a free body diagram? Now, in some cases here, they're referring back to previous tactics boxes. Now, obviously, this is a tactics box from the book, so if you have access to the book, you can also just flip back a few pages and look at these. If you don't have access to the book, I have included these in previous videos. So, and these are other videos from Chapter 5. So the first thing you need to do is identify all of the forces. And again, this is on one object. If you have more than one object you're concerned about, and this will come up in Chapter 7, you need to draw more than one free body diagram. So one free body diagram equals one object. Now, the one caveat to this is if, for instance, you have a car and there's people in the car, then your object is, say, the car and the people in it. You don't necessarily need to draw separate ones for the people. if you're just considering the whole motion. So one object could actually mean a conglomeration of things that are moving together. That's okay, right? If you have a box full of puppies sliding down a ramp, you don't have to draw a separate free body diagram for every single puppy. Your object in that case is the box of puppies. So first step is identify all of the forces. And this step was previously described in a tactics box. And the idea of that tactics box was to basically draw a sketch of the situation and then confine what is your object by drawing a circle around it, and then identify everything interacting with it and identify the forces. And we will do some examples that actually do this. Step 2 is draw a coordinate system. Now this is important, and you should be defining a coordinate system anytime you're dealing with, ideally, even one-dimensional motion, but certainly two-dimensional motion. So in this case, if you have a pictorial representation, you should have drawn axes, and your free body diagram should have consistent axes. So make sure that you're using one consistent set of axes for all of your visual representations, however you've chosen to do them, and then all of your calculations. Now here it says represent the object as a dot at the origin of the coordinate axes. Now this is one of the few places that I actually work a little bit differently than the book. Now you are welcome to always use a dot. Where I do something different is, let's say you have a box on a ramp, right? So this would basically be your sketch. So we have a box on a ramp. Now when I go to draw my free body diagram, instead of just doing a dot, which can make it hard to figure out what that angle is, I sometimes will actually draw my tilted box, just so you still kind of have that orientation. Now, if you draw just the dot, then you might want to actually draw that surface. If you draw the box, then you kind of have that surface defined, and you can draw things that are perpendicular to it, things that are down, etc. So if you do use the dot, you want to do something to represent what the ramp surface is, the angle. And again, you might do a dashed line, but it needs to be very clear that itself is not a force. You might use your axes labels to represent that, but I'll typically draw a box in that case to kind of just give me some orientation. So feel free to do that either way. Next, draw vectors representing each of the identified forces. And again, this is something that the book has already shown. And in this case, these should be coming from the center. So in this case, you see that they're still coming from the center, even though it's a box. So make sure here that this is from the center. And the one caveat is that when we get to chapter 12, they might come from different places on the object, or sorry, act on different places on the object, but that's chapter 12 when we get to rotation. Lastly is to draw and label the net force. Now, one thing that it says here that is very, very important is to draw this beside the diagram. Don't draw it coming from the center as if it is a separate force. The net force is just the vector sum of all of the forces. Now, if there is no net force, and again, you might know that there's no net force because it might be in equilibrium, you should write F net equals 0, okay? And if your F net is not 0, you want to make sure that the direction agrees with the acceleration. Now in this case, it's saying the acceleration on your motion diagram. It might make sense to draw a motion diagram. It might make sense to have, plot of acceleration in a certain direction. Whatever you choose to do, make sure that your net force and your acceleration agree. So I want to do some examples on this rather than just giving you the list of instructions, but I do encourage you to come back and actually reference these instructions, because if you're new to drawing free body diagrams, you might forget these steps, or you might do them in the wrong order. If you have done free body diagrams before, be careful. I am going to be fairly strict about this, so please make sure that you're drawing these the right way and that you're not just being sloppy about it and drawing a bunch of arrows on a page.